Hello, abstract algebra students. This begins lecture 1.5 on semigroups of subsets. Normally, this lecture is the Wednesday of the second week of the semester. This lecture will have a foundations feel to it as we take the set theory that we learned in foundations and we give it an abstract algebra lens. So we start by looking at our algebraic structure. We need a new algebraic structure, and remember, an algebraic structure consists of a set, a notion of equality, and an operation. So here we go. We are going to suppose that M is a non-empty set. Now, the set that will become our algebraic structure is something called the power set. It's called the power set of M. And I'll boldface the power set because that's the words that we're trying to define. Denoted by P of M is the set of all subsets of M. Now, we can write this as P of M is the set of all capital A such that A is a subset of M. Now, let's look, before we get any further, let's look at some examples of this definition. What do I mean by the power set? Well, if M were the set containing just the numbers 1, 2, there are 4 subsets of this, the set containing 1, 2. And to find the subset, remember, you have to first ask, do you want 1 to be in the subset? And then do you want 2 to be in the subset? So there are 4 subsets of M, one of which is the empty set, which consists of neither 1 nor 2. One is the set containing just the number 1. One is the set containing just the number 2. And one is the whole set M containing both 1 and 2. Now, any set has the null set and the set itself as subsets. Sets can also have other subsets that are in between the null set and the set itself. Here, for example, would be the set containing just 1 and the set containing just 2. If we take this one step further, if M is the set containing 1, 2, 3, then P of M now I'm going to list them carefully to make sure I get them all. First of all, we'll look at the subsets that have 0 elements. That's just the null set. Now we'll look at the subsets that each have 1 element. Those are the sets containing 1, 2, and 3. Now we'll look at the sets that have 2 elements. So the set containing 1 and 2, the set containing 1 and 3, the set containing 2 and 3. Those are the sets that have 2 elements. And then M, the whole set, is the set that contains 3 elements. So notice here, if M had 2 elements, it had 4 subsets. And if M had 3 elements, then it had 1, 2, 3, 4, 5, 6, 7, 8 subsets. And we proved in foundations that in general, if a set has n elements, it has 2 to the n subsets. Okay, so what we're going to do now is we're going to look at these sets of subsets and we're going to try to make an algebraic structure out of them. So now we need a notion of equality. So two sets A and B are equal. Denoted by A equals B, when for every X, X is in A if and only if X is in B is true. Now, this is the same thing. This is the same thing as saying two sets are equal when they have precisely the same elements. It is also the same thing as saying two sets are equal when X is a member of A is logically equivalent to X is a member of B. Now, finally, I want to talk about various operations on the power set. So there are three operations that I want to look at. Two of them you have seen before from foundations, the intersection and union. So the intersection of A and B is set of all X such that both X is a member of A and X is a member of B. Set of all X such that both X is a member of A and X is a member of B. Now, the union of A and B is A union B is the set of all X such that either X is in A or X is in B. These two things we've seen from foundations. Now remember, or here means the inclusive or. And I can get a new set if I look at the symmetric difference. So the symmetric difference of A and B is A, so we'll use a triangle for symmetric difference, is the set of all X such that either X is in A or X is in B, but not. And we can also write this equivalently as using what we know about logical equivalence from foundations. We can write this as asymmetric difference B is, now we think. If X is in either A or B, but not both, it means either both X is a member of A and X is not a member of B. Or both, X is not a member of A and X is a member of B. If you're in either A or B but not both, it means either you're both in A and not B, or both you're not in A and you're in B. Okay, so these are the operations. More to follow.